Out there, drifting in the frigid darkness beyond Neptune, spins one of the strangest objects our solar system has ever revealed, a cosmic oddity so bizarre it defies everything we thought we knew about dwarf planets. Meet Haumea, a world unlike any other, shaped more like a squashed football than a sphere, spinning so fast it completes a full rotation in less than 4 hours, and surrounded by a pair of mysterious moons and a faint, ghostly ring. This isn't just another frozen rock in the Kuiper Belt, it's a scientific puzzle wrapped in an enigma, challenging our understanding of how celestial bodies form and evolve. And the deeper we look, the more questions it raises. Why does it spin so recklessly? How did it end up with such a strange, elongated shape? And what secrets lie beneath its icy surface? For years, Haumea has been the black sheep of our solar system, a cosmic outlier that refuses to fit neatly into any category. Discovered in 2004, it quickly became clear this wasn't just another Pluto-like world. Its extreme speed, its peculiar family of smaller objects trailing behind it, even its glittering crystalline ice surface, all of it hints at a turbulent past, a history of violent collisions and cosmic drama we're only beginning to piece together. Some scientists suspect it might even be a remnant of an ancient, catastrophic smash-up, a survivor of a long-forgotten battle in the depths of space. But the mystery doesn't stop there. Haumea's strangeness isn't just about its shape or its spin, it's about what it tells us, or rather, what it refuses to tell us. Why does it have a ring when almost no other objects in its neighborhood do? How did its 2 moons end up in such peculiar orbits? And what hidden forces are still at work in the dark, frozen reaches of the Kuiper Belt, sculpting worlds into shapes we never expected? Today, we're diving into 25 of the most baffling, mind-bending mysteries surrounding Haumea, questions that push the limits of our knowledge and force us to rethink what we thought we knew about the outer solar system. This isn't just a tour of a weird little world. It's a journey into the unknown where every answer leads to a dozen new questions, and by the end, you'll see why Haumea might just be the most fascinating object you've never heard of. Haumea's bizarre shape is the first clue that something extraordinary happened in its past. While most dwarf planets like Pluto or Eris are nearly spherical, Haumea looks like it was stretched sideways, flattened into a shape resembling a squashed football or a spinning top. Scientists call it a triaxial ellipsoid, meaning it has 3 distinct axes of different lengths, making it one of the most elongated known objects in our solar system. But how does a world end up looking like this? The answer lies in Haumea's breakneck rotation. It completes a full spin in just 3.9 hours, faster than any other known dwarf planet. That speed creates immense centrifugal force, flinging material outward at the equator and squashing the poles inward. But here's the catch: current models suggest this spin alone shouldn't be enough to stretch Haumea this dramatically. Something else must have given it that extra push. One leading theory points to a catastrophic collision billions of years ago. Imagine 2 massive icy bodies slamming into each other with unimaginable force, a hit so violent it sent debris flying and left Haumea tumbling wildly, its rotation sent into overdrive. This might also explain the strange family of smaller objects sharing similar orbits, possibly fragments from that ancient crash, but not everyone's convinced. Some researchers argue Haumea's spin could have built up gradually over time, influenced by the gravitational tug of Neptune or even interactions with its own moons. Yet neither theory perfectly accounts for the sheer extremes we observe. If collisions shaped it, why don't other Kuiper Belt objects show similar warping? And if it spun up slowly, why hasn't gravity smoothed it back into a more rounded shape? The mystery deepens when we look at the numbers. Haumea's longest axis stretches about 2,100 kilometers, roughly the distance from New York to Las Vegas, while its shortest is barely half that. That kind of distortion defies even our most advanced simulations. every tweak to the models either leaves Haumea too round or rips it apart entirely. It's as if we're missing a crucial piece of the puzzle, some hidden factor that tipped the scales in this cosmic balancing act. Could there be exotic materials in its interior reinforcing its structure, or did multiple collisions sculpt it in ways we haven't yet imagined? Until we get closer, until a spacecraft finally visits this strange world, Haumea's peculiar shape remains one of the solar system's most tantalizing riddles. The violent history that might explain Haumea's bizarre shape becomes even more fascinating when we examine the competing theories about what exactly happened out there in the dark. The leading hypothesis suggests a monumental collision, a cosmic car crash so powerful it didn't just alter Haumea's shape but also created its two moons, Hiyoka and Namaka. Picture this: two massive icy bodies, each potentially half Haumea's size, slamming together at thousands of kilometers per hour. The energy released wouldn't just spin Haumea faster, it would vaporize ice, fracture rock, and hurl debris into space, some of which could have clumped together to form those moons. But here's where things get tricky. For an impact to stretch Haumea this dramatically while also launching material into stable orbits, the collision would need near-perfect conditions. A precise angle, just the right speed, and objects with very specific compositions. Even a slight variation, and you'd end up with a scattered debris field rather than a neat system of moons. What's even stranger is that the energy required for this kind of event pushes the limits of what we'd expect in the Kuiper Belt. Most objects out there move relatively slowly, drifting through space like lethargic icebergs. A collision violent enough to reshape Haumea would require speeds or object sizes that don't quite match our current understanding of the region's dynamics. Some researchers argue that perhaps Haumea wasn't born in the Kuiper Belt at all, that it might be an interloper from somewhere else, flung outward by gravitational chaos in the early solar system. Others speculate that multiple smaller impacts, rather than one giant smash, could have gradually spun Haumea up to its current dizzying speed. But this raises another puzzle. Why don't we see similar warping on other Kuiper Belt objects? If collisions were common enough to sculpt Haumea, why is it seemingly the only one twisted into such an extreme shape? The moons themselves add another layer of mystery. Hiyoka, the larger of the two, orbits Haumea in a nearly circular path, while Namaka follows a far more eccentric, tilted trajectory. This mismatch suggests they didn't form under calm, orderly conditions. If they were born from the same impact, why such different orbits? One possibility is that Haumea's rapid spin and irregular gravity tugged them into these unusual paths over time. Another tantalizing idea is that Namaka might be a second-generation moon, a fragment of a moon that itself broke apart after the initial collision. There's even evidence that Hiyoka's surface is covered in crystalline ice, which typically requires internal heat to form. Could tidal forces from Haumea's gravity have melted its interior at some point? Or does this hint at yet another ancient impact we haven't accounted for? Every explanation seems to open new questions. The more we study Haumea's family of objects, the clearer it becomes that this wasn't a simple accident. It was a cascade of violence, a series of events so finely balanced that recreating them in simulations often ends in digital rubble. Some models suggest the impactor would have needed to be nearly as large as Haumea itself, which makes the odds of such an encounter staggeringly low. Others propose that Haumea's composition, possibly a mix of rock and ice with unusual structural properties, allowed it to stretch rather than shatter under extreme forces. But without direct measurements, these ideas remain educated guesses. What we're left with is a cosmic crime scene billions of years cold, where the clues are written in spinning ice, tilted orbits, and a shape that defies the rules. Until we send a probe to study Haumea up close, its origin story will remain one of the solar system's most compelling unsolved mysteries. Haumea's breakneck rotation isn't just unusual, it's downright physics-defying. Clocking in at a mere 3.9 hours per day, This dwarf planet spins faster than any other known object of its size in the entire solar system. To put that into perspective, Earth takes 24 hours to complete one rotation. Jupiter, the solar system's speed demon, whirls around in just under 10 hours. But Haumea, it makes them both look sluggish. If you stood on its surface, assuming you could find a spot to stand on its wildly stretched equator, you'd witness a sunrise and sunset every hour and 56 minutes. But how does something this massive spin so recklessly without tearing itself apart? The answer lies in angular momentum, one of the universe's most fundamental laws. When an object spins, its mass and velocity create a kind of cosmic inertia that resists change. For small bodies like asteroids, rapid rotation isn't surprising. Their tiny size makes it easier to spin fast. But Haumea is over 1,000 kilometers wide, with an estimated mass 1/3 that of Pluto. At that scale, the forces at play should have either slowed it down over time or ripped it to shreds. Yet here it is, whirling like a cosmic top with no signs of stopping. This presents astrophysicists with what's known as the missing angular momentum problem. Where did Haumea get all that spin energy, and why hasn't it dissipated? One possibility is that Haumea was born from chaos. If a colossal impact spun it up billions of years ago, the debris flung outward might have carried away enough energy to leave Haumea balanced on the knife's edge between stability and destruction. But simulations struggle to recreate this scenario without the planet either flying apart or settling into a slower rotation. Another theory suggests Haumea might have been nudged into its dizzying dance by gravitational interactions. Perhaps a close encounter with Neptune or another massive Kuiper Belt object gave it an extra kick. But these events are rare, and the odds of one leaving Haumea spinning precisely this fast are astronomically low. Even more perplexing is what keeps Haumea intact. Most rapidly rotating bodies flatten into oblate spheroids, like a pizza dough spun in the air. But Haumea's extreme elongation suggests its interior structure must be unusually rigid, possibly reinforced by a dense rocky core or a unique arrangement of ice and minerals. Some researchers speculate that its high albedo surface covered in reflective crystalline ice could be a clue. This ice might have once been molten, reshaping itself under centrifugal forces before refreezing into a stretched, stable shell. Yet without seismic data or close-up imagery, these ideas remain speculative. The implications ripple beyond Haumea alone. If such rapid rotation can persist in a body this size, it challenges our assumptions about how celestial objects behave. Could there be other hyper-fast dwarfs lurking in the Kuiper Belt, overlooked because their strange shapes don't match our expectations? And what does Haumea's survival tell us about the limits of planetary formation? Every unexplained detail makes this tiny world a giant question mark, forcing us to reconsider the rules we thought governed the cosmos. Until we can study it up close, Haumea's spin remains a mesmerizing defiance of the universe's ordinary rhythms. Just when we thought Haumea couldn't get any stranger, astronomers made a discovery that sent shockwaves through the scientific community. In 2017, during a stellar occultation, when Haumea passed in front of a distant star, researchers detected something utterly unexpected. A faint but unmistakable ring encircling this already bizarre world. This wasn't just surprising, it was revolutionary. Rings are supposed to be the exclusive domain of gas giants like Saturn or Uranus, not tiny, misshapen dwarfs spinning at breakneck speeds. Haumea's ring defies every rule we thought we knew about how and where these cosmic halos form. The ring itself is a narrow, dense band of particles orbiting about 1,000 kilometers above Haumea's surface. Measurements suggest it's roughly 70 kilometers wide, with particles likely ranging from dust-sized grains to boulders. But here's the real head-scratcher. Conventional wisdom states that rings form when moons or other large bodies get too close to their parent planet and are torn apart by tidal forces. The debris then spreads out into a flat disk, eventually settling into the elegant rings we see around Saturn. but Haumea's extreme rotation and irregular shape should make this impossible. Its gravitational field isn't uniform, it's lumpy and uneven, with wild variations due to its elongated form. Any ring material should have been flung into space or pulled down to the surface long ago. So how did this delicate structure survive? One theory suggests the ring might be a relic of the same ancient collision that shaped Haumea's body and birthed its moons. If the impact was violent enough to hurl debris into orbit, some of it could have settled into a stable ring before Haumea's spin could disrupt it. But this raises another question. Why hasn't the centrifugal force from Haumea's rapid rotation scattered the particles over billions of years? Some researchers propose that the ring might be younger than we think, possibly replenished by ongoing micrometeorite impacts on Haumea's moons or even subsurface activity ejecting fresh material into orbit. Others speculate that Haumea's unique gravitational quirks, its lumpy, potato-like shape, might have created unexpected stable zones where ring particles can persist. Even more puzzling is the ring's composition. Unlike Saturn's icy rings, Haumea's appears darker and more reflective, hinting at a mix of ice and organic compound. Could chemical reactions on its surface be feeding the ring with new material? Or does this suggest the ring formed from a different process entirely, perhaps a captured fragment of a passing comet or Kuiper Belt object? Every explanation seems to introduce new contradictions. If rings require calm, orderly conditions to form, how did one arise around a world that's essentially a cosmic demolition derby? The implications stretch far beyond Haumea. If rings can exist around such extreme objects, it forces us to reconsider how common they might be in the outer solar system and beyond. Could other dwarf planets or even rogue planets drifting between stars harbor hidden rings of their own? Haumea's stubborn refusal to play by the rules reminds us that the universe is far stranger than our textbooks suggest. Until we can study this enigmatic ring up close, its very existence remains a dazzling challenge to our understanding of celestial mechanics. Haumea's moons, Heoka and Namaka, shouldn't exist, at least not the way we see them today. These tiny companions, born from what scientists believe was a cataclysmic collision, have a composition that defies logic. When astronomers analyzed their surfaces using spectroscopy, they found something astonishing. Both moons reflect light with the unmistakable signature of nearly pure water ice, with almost no contamination from dust or organic material. This pristine ice is bizarre because it contradicts everything we know about cosmic collisions. When objects smash together in space, the debris is typically messy, a chaotic mix of shattered rock, dark carbon compounds, and jumbled ice. Yet here are two moons that look like they've been carved from glaciers and polished by unseen hands. The purity of their ice raises two glaring questions. First, how did material from a violent impact end up so clean? When celestial bodies collide, the energy vaporizes ice and pulverizes rock, creating a fog of debris that should have left Haumea's moons coated in a mix of minerals and sooty organic residues. Instead, Heoka and Namaka gleam like cosmic snowballs, their surfaces reflecting over 90% of the sunlight that hits them, far brighter than most objects in the Kuiper Belt. One theory suggests that the impact that formed them might have been unusually clean, vaporizing only the icy outer layers of Haumea while leaving its rocky core intact. The ejected ice could have condensed into pure crystals before reaccumulating into moons, but this requires a perfect, almost surgical collision, something statistically unlikely in the chaotic early solar system. Even more baffling is why these moons haven't accumulated dust over billions of years. The Kuiper Belt isn't empty, it's filled with micrometeorites and dark organic particles drifting through space. Over time, these should have settled onto the moon's surfaces, dimming their brilliance, yet they remain startlingly bright. Some researchers propose that tidal heating from Haumea's gravity might have caused occasional resurfacing melting subsurface ice that erupted in cryovolcanic flows, covering older, dirtier layers with fresh ice. But there's little evidence of such activity today, and Namaka's small size makes internal heating unlikely. Another possibility is that the moon's orbits keep them in a kind of gravitational sweet spot, where Haumea's uneven pull deflects incoming debris. But this still doesn't explain why similar protection hasn't been observed around other Kuiper Belt moons. Then there's the mystery of crystalline ice. The ice on Hioka and Namaka isn't just pure, it's structured in a highly ordered crystalline form, which typically requires temperatures above -150 degrees Celsius to form. That's far warmer than the Kuiper Belt's current frigid conditions, where temperatures hover near -230 degrees. This suggests that at some point, the moons were warm enough to melt or at least soften their ice, allowing molecules to rearrange into neat lattices. But how? The usual suspects, radioactive decay or tidal heating, don't seem sufficient given the moon's small sizes. Some scientists speculate that the impact that created them generated enough heat to briefly liquefy their surfaces before they refroze into crystalline sheets. Others wonder if ancient sunlight, when the solar system was younger and Haumea's orbit might have been closer to the sun, played a role. The contradictions pile up with every observation. If the moons formed from a messy collision, why are they so pristine? If they've existed for billions of years, why haven't they darkened like every other ancient surface in the solar system? And if they're geologically dead now, how did their ice ever get warm enough to crystallize? Each answer only deepens the enigma, painting Haumea's moons as cosmic anomalies that challenge our understanding of how planetary systems evolve. Until a spacecraft visits this distant family, their gleaming surfaces will remain one of the solar system's most confounding puzzles, proof that even in the frozen fringes of our cosmic neighborhood, nature still has surprises up its sleeve. Bursting onto the scene as one of the solar system's most unusual clans, Haumea's Collisional family is a cosmic detective story written in ice. Astronomers have identified over a dozen Kuiper Belt objects sharing nearly identical spectroscopic fingerprints, crisp, bright water ice signatures that mirror Haumea and its moons with uncanny precision. These scattered fragments, strewn across millions of kilometers, are thought to be shrapnel from the same ancient catastrophe that stretched Haumea into its football shape. But the plot thickens when you examine their positions and movements. Their distribution is all wrong, like a crime scene where the evidence refuses to line up with the suspect's alibi. Computer simulations of the proposed giant impact keep hitting the same wall. The family members are too spread out, moving too fast, and clustered in ways that defy the physics of a single, violent event. Take their velocities first. When objects are blasted apart in a collision, debris typically follows predictable patterns like shards from a broken vase. They fan out with speeds proportional to the explosion's force. Yet Haumea's family displays a chaotic spread, with some fragments drifting sluggishly while others race away as if given an extra kick. Some models suggest gravitational nudges from Neptune could account for this, but the timing doesn't add up. The gas giant's influence would have either scattered the family completely or left them more tightly grouped, not this odd middle ground. Other theories propose that multiple impacts might have contributed to the family over time, like successive hammer blows chipping pieces off Haumea. But then, why do all the fragments share nearly identical ice compositions? Normally, repeat collisions would introduce material from different sources, muddying the spectral signatures. Then there's the spatial arrangement. The family members aren't neatly arrayed along Haumea's orbital path as expected. They're clumped in unexpected pockets, with puzzling gaps between them. One cluster sits surprisingly close to Haumea, while another group lurks much farther out. This isn't just a clean debris field, it's more like a thrift store jumble of mismatched pieces. Dynamicists have tried tweaking every variable: impact angle, projectile size, even the possibility of Haumea once having a different orbit, but no simulation satisfactorily recreates the family's current disarray. Some researchers speculate that resonances with Neptune's gravity might have shepherded fragments into these strange groupings over eons, like an invisible hand arranging cosmic marbles. Yet even this elegant idea can't fully explain why certain zones remain empty while others are crowded. The ice itself adds another complication. Every confirmed family member reflects sunlight with the same telltale shimmer of pure, crystalline water ice, a match so precise it's as if they were all carved from the same glacier. This level of compositional purity is staggering considering the Kuiper Belt's usual mishmash of ices and organics. It suggests the impact must have excavated material from a specific, homogeneous layer beneath Haumea's surface, blasting it into space before contaminants could mix in. But this demands an almost surgical strike: too shallow and you'd scoop up surface gunk, too deep and you'd dredge up darker subsurface material. Getting it just right implies Haumea's interior was bizarrely stratified, with a pristine ice shell overlying its rocky core like a cosmic layer cake. Perhaps the most tantalizing clue lies in what's missing. The family should include a spectrum of fragment sizes from mountain-sized chunks down to dust, but observations show a curious absence of mid-sized objects. It's as if someone selectively removed certain pieces from the puzzle. Could some fragments have been pulverized by later collisions, or does this gap hint that the family formed through a different mechanism entirely, like a partial disintegration from Haumea's extreme spin rather than a single outside impact? Every hypothesis seems to unravel at the edges, leaving more threads dangling than answers. This isn't just academic nitpicking. Haumea's family paradox forces us to reconsider how collisions sculpt the outer solar system. If our models can't recreate this event, what else might we be getting wrong about the Kuiper Belt's violent past? The discrepancies suggest gaps in our understanding of everything from impact physics to ice chemistry in the deep freeze of space. Until a dedicated mission can study Haumea and its kin up close, these icy outliers will remain both evidence and enigma, a frozen snapshot of chaos that refuses to fit neatly into any theoretical box. Haumea doesn't just stand out for its shape and spin. It's also one of the shiniest objects in the solar system, gleaming like a cosmic disco ball in the frozen darkness. With an albedo, a measure of reflectivity between 0.7 and 0.8, its surface bounces back more sunlight than freshly fallen snow on Earth. To put that in perspective, Pluto, its neighbor in the Kuiper Belt, reflects just 40 to 50% of the light that hits it. Even Saturn's dazzling rings don't match Haumea's brilliance. This raises a glaring question. How does a tiny, distant world, bombarded by cosmic rays and micrometeorites for billions of years, maintain such a pristine, mirror-like surface? The answer likely lies in what's covering Haumea: vast expanses of crystalline water ice. Unlike the amorphous, jumbled ice found on many cold celestial bodies, crystalline ice has an orderly molecular structure that scatters light with exceptional efficiency. But here's the catch: crystalline ice is fragile. Cosmic radiation and temperature fluctuations should have broken it down into a darker, less reflective form over time. The fact that Haumea's surface remains so bright suggests something is actively renewing it, like an invisible hand polishing the ice before it can tarnish. One possibility is cryovolcanism, eruptions of water or slushy ice from beneath the surface, but Haumea's small size and lack of obvious heat sources make sustained geological activity unlikely. Another theory points to its insane rotation speed. The constant centrifugal force might be flinging fresh ice particles from fractures or geysers up onto the surface, creating a self-replenishing glaze. Complicating matters is Haumea's temperature. At nearly -230 degrees Celsius, its surface is far too cold for liquid water or even soft ice to exist. Yet crystalline ice typically forms at warmer temperatures, meaning Haumea's ice must have been heated at some point before freezing into its current state. Some researchers speculate that past tidal heating generated by gravitational interactions with its moons could have temporarily warmed subsurface layers enough to reorganize the ice molecules. Others wonder if ancient impacts fractured the crust, releasing pockets of volatile compounds that refroze into reflective sheets. But none of these explanations fully account for the sheer scale of Haumea's reflectivity. Current thermal models predict that even with occasional resurfacing, its ice should have darkened significantly over billions of years as radiation baked its surface into a duller state. The persistence of such high albedo hints at processes we haven't yet imagined. Perhaps exotic chemistry involving methane or nitrogen ices mixing with water to create a self-cleaning surface, or electrostatic forces levitating fine ice particles to form a constantly refreshing top layer. The implications ripple beyond Haumea. If such extreme reflectivity can persist in the Kuiper Belt's harsh environment, it forces us to rethink how surfaces evolve on icy worlds. Could other distant objects hide similarly pristine ice beneath darker exteriors? And what does Haumea's brilliance tell us about the early solar system's conditions? Every unanswered question makes this tiny, glittering world a beacon, not just of reflected sunlight, but of the enduring mysteries lurking at the edge of our cosmic backyard. If there's one thing that makes Haumea truly unpredictable, it's the way this distant world radiates heat. Infrared observations have revealed a thermal light curve that defies all expectations, a pattern of temperature variations so erratic, they seem to dance to their own mysterious rhythm. Unlike most celestial bodies where surface temperatures sync neatly with rotation periods, Haumea's heat signature flickers like a candle in the wind, with hot spots appearing and vanishing without explanation. This isn't just a quirk, it's a full-blown scientific revolt against how small, icy worlds are supposed to behave. At the heart of the puzzle is a glaring mismatch. Haumea spins every 3.9 hours, yet its hottest regions don't align with its rotation. Some areas stay stubbornly warm while others chill rapidly, as if hidden furnaces pulse beneath the ice. One leading theory points to subsurface heat conduction gone haywire. Most dwarf planets transfer heat evenly, like a potato baking in an oven. But Haumea's elongated shape and possible internal fractures could create thermal highways, as zones where heat races to the surface while neighboring regions remain freezing. Imagine a frozen lake with random patches of thin ice where warmth bleeds through, except here, the lake is a dwarf planet and the warmth might hint at geological unrest. The wild card in this thermal puzzle, cryovolcanism. While most scientists dismissed the idea of active eruptions on such a small, cold body, Haumea's temperature spikes have forced a reconsideration. Could pockets of slushy ammonia water mixture, a natural antifreeze, survive deep underground, occasionally bursting through cracks in the ice shell? These hypothetical eruptions wouldn't spew lava, but a frigid slurry that flash freezes into fresh, reflective ice, potentially explaining both the thermal anomalies and Haumea's bizarrely bright surface. There's even tantalizing evidence that certain hotspots correspond to regions where gravitational stress from Hioka and Namoka might flex Haumea's crust, generating friction heat. But not everyone's convinced. Alternative explanations range from the mundane to the extraordinary. Some argue that variations in surface texture, patches of coarse versus fine ice, could create the illusion of temperature swings by radiating infrared light differently. Others whisper about the possibility of exotic materials with unusual thermal properties lurking beneath the surface, like clathrate hydrates, ice-like compounds that trap gases and release heat when disturbed. Then there's the radical notion that Haumea's interior might still harbor residual warmth from its violent formation, with heat trickling upward through a fractured mantle like steam through a maze of pipes. The implications stretch beyond academic curiosity. If Haumea does host cryovolcanic activity, it would rewrite the rules for what small, distant worlds can do. Active geology was supposed to require either a hefty size like Pluto or tidal heating from a nearby giant planet like Jupiter's moon Europa. Yet here's Haumea, a misfit dwarf, potentially defying both requirements. And if the heat comes from something else entirely, that could hint at processes we haven't even named yet, lurking undetected in the solar system's frozen fringes. Until we can peer beneath its glittering ice shell, Haumea's thermal tantrums will remain one of the most confounding mysteries in planetary science, a reminder that even in the coldest corners of space, things aren't always as dormant as they seem. Haumea's lack of an atmosphere is one of its most perplexing contradictions. Unlike Pluto, which puffs up a temporary nitrogen haze when it swings closer to the Sun, or even distant Eris, where methane might sublimate into a whisper-thin seasonal cloak, Haumea remains stubbornly bare. No detectable gases, no fleeting frosty exhalations, just empty space hugging its icy surface. This absence is baffling because by all accounts, Haumea checks every box for atmospheric potential. It's coated in water ice, which should vaporize under solar radiation. Its rapid rotation creates temperature extremes that could drive sublimation. And if thermal anomalies hint at underground warmth, why isn't that energy cracking the ice and venting gases into the void? The mystery deepens when you compare it to its Kuiper Belt neighbors. Pluto's tenuous atmosphere, though faint, blooms as sunlight transforms surface ices directly into gas, a process we've observed repeatedly. Even smaller objects like Makemake show traces of transient methane atmospheres during their closest solar approaches. Yet Haumea, with a surface composition and orbit that should make it a prime candidate for outgassing, sits eerily silent. One theory suggests that Haumea's extreme spin might be the culprit. The same centrifugal forces that flattened its shape could be flinging any liberated molecules into space before they can accumulate into a stable envelope. Imagine trying to fill a balloon with a hole torn in its side. Particles escape as fast as they're released, but there's a problem with this explanation. Other fast-spinning bodies, like Saturn's moon Hyperion, still manage to hold onto thin atmospheres despite their dizzying rotations. The difference might lie in Haumea's unique ice chemistry. Its surface appears dominated by crystalline water ice, which requires more energy to sublimate than the nitrogen or methane ices coating Pluto. Even if sunlight warms Haumea's surface, the temperatures might never climb high enough to break water molecules free en masse. Some researchers propose that any gases that do escape could be instantly frozen back onto the surface by the relentless cold, creating an invisible cycle of capture and release too subtle for our telescopes to detect. Then there's the possibility that Haumea's internal heat, if it exists, isn't reaching the surface in the right way. On Pluto, geothermal warmth percolates through cracks and vents, feeding its atmosphere. If Haumea's heat is locked beneath an unusually thick or insulating ice layer or distributed too evenly, it might not create the pressure needed to breach the surface. Alternatively, its heat could be channeled toward maintaining its crystalline ice structure rather than vaporization. The most tantalizing and controversial idea is that Haumea might have once had an atmosphere but lost it in a catastrophic event. A massive impact could have blasted away volatile compounds, leaving it permanently desiccated, or gravitational jostling might have altered its orbit long ago, placing it in a deeper freeze where gases couldn't recover. Either scenario would make Haumea a tragic case of cosmic climate collapse, a world that squandered its atmospheric potential in a single violent moment. Until we can study Haumea up close, its airless state remains a gap in our understanding of how small, icy worlds breathe. Is it a question of chemistry or physics or pure chance? The answer might rewrite how we define the boundary between a dynamic dwarf planet and a frozen, inert relic. One thing's certain, in a solar system where atmospheres come and go, Haumea's silence speaks volumes. Haumea's surface is a blank slate that shouldn't exist. Despite intense scrutiny from Earth-based telescopes and the Hubble Space Telescope, not a single definitive crater has been spotted on this rapidly spinning dwarf planet. This absence of surface features isn't just unusual, it's nearly impossible given what we know about the Kuiper Belt's violent history. Consider that Pluto, Haumea's neighbor, bears scars from countless impacts across its ancient terrain. Even tiny, smooth-surfaced moons like Saturn's Enceladus show at least some cratering. Yet Haumea presents a pristine, featureless face to the universe, as if someone took a cosmic eraser to its entire surface. The implications are staggering. Either Haumea has somehow avoided being struck by asteroids and comets for billions of years, statistically absurd in the bombardment-prone outer solar system, or something is actively wiping away the evidence. The most plausible explanation points to ongoing resurfacing, where internal processes renew Haumea's exterior faster than impacts can mark it, but this raises more questions than answers. On icy worlds like Jupiter's Europa or Saturn's Enceladus, geological activity comes from tidal heating, the gravitational kneading of a nearby giant planet. Haumea has no such energy source. Its small size and lack of close planetary neighbors should make it geologically dead. One radical theory suggests Haumea's extreme rotation could be powering its own resurfacing. The same centrifugal forces that stretched it into an ellipsoid might generate enough internal friction to melt subsurface ice periodically. Imagine a world where the entire crust periodically becomes unstable, with sections sliding like tectonic plates on a lubricated surface. Fresh ice could well up from below, filling in craters before they have time to accumulate. Supporting this idea are faint hints of linear features in some observations, possible fault lines or fractures where material might emerge. Alternatively, Haumea's surface might be unusually fragile. If composed of loosely packed ice crystals or fluffy snow-like material, impacts could create temporary depressions that gradually heal as the material flows back. This would explain both the lack of craters and the high reflectivity. Fresh snow reflects more light than compacted ice. Some laboratory experiments with cryogenic ices show similar behavior, where even tiny temperature changes cause dramatic structural shifts. The mystery compounds when we consider timescales. Crater counts are how planetary scientists estimate surface ages. More craters mean older terrain. A completely uncratered surface suggests geological resurfacing within the last 100 million years at most. Yet nothing in our current models predicts such recent activity on an isolated dwarf planet. Either we're missing a fundamental energy source in the Kuiper Belt, or Haumea possesses some exotic self-renewing mechanism we've never encountered before. Perhaps the most mind-bending possibility is that Haumea's surface isn't solid at all, but rather a dynamic slurry maintained by its spin. At its rotation speed, loose surface material would experience near weightlessness at the equator, potentially creating a constantly shifting quicksand of ice particles that swallows impact marks. This could explain both the lack of features and the thermal anomalies. Such a mobile surface would redistribute heat in unpredictable ways. Until we can study Haumea up close, its smooth countenance remains one of the solar system's most confounding optical illusions. A world that looks brand new despite dating back to the dawn of planetary formation. Whether through hidden energy, exotic materials, or some undiscovered process, Haumea continues to defy our expectations, proving that even in the frozen depths of space, change and renewal might be happening right under our telescopes if only we knew where to look. Haumea's surface defies one of space's most fundamental rules, that no terrain remains unchanged forever. While most airless bodies show patchwork surfaces scarred by space weathering, cosmic rays, and micrometeorite impacts, Haumea presents an eerie uniformity. Spectroscopic studies reveal nearly identical water-ice signatures across its entire surface, as if someone took a celestial paint roller to this dwarf planet. This spectral sameness exists despite conditions that should create dramatic regional differences, extreme temperature swings between its sunlit and shadowed sides, varying exposure to solar wind, and potential cryovolcanic activity. On any other world, these factors would produce a mottled quilt of altered and fresh ice. Yet Haumea stubbornly maintains its flawless facade. The leading explanation, and perhaps the most controversial, centers on a process called global ice convection. Imagine Haumea's outer shell behaving like a simmering pot of water, with warmer ice slowly rising from below while colder surface material sinks. This constant recycling could theoretically refresh the entire surface every few 100 million years, erasing chemical variations before they can accumulate. The concept draws parallels to Earth's mantle convection or even the lava lamps of the 1960s, where heat-driven movement creates a self-renewing system. But here's where the physics gets shaky. For convection to work on Haumea, its ice layer would need properties bordering on the impossible, simultaneously rigid enough to maintain the dwarf planet's extreme shape, yet pliable enough to flow on geological timescales. Laboratory experiments with high-pressure ices show some materials might pull off this paradoxical behavior under specific conditions. Certain crystalline ice phases, like Ice 6 or Ice 7, exhibit strange plastic qualities when subjected to the right mix of temperature and stress. If Haumea's interior contains these exotic ices, combined with trace amounts of ammonia or salts acting as antifreeze, convection becomes theoretically plausible. Yet even these exotic materials struggle to explain the uniformity scale. Convection cells typically create distinct regions of upwelling and downwelling, which should appear as subtle spectroscopic variations, exactly what we don't see on Haumea. Alternative theories scramble to fill the gaps. One suggests Haumea might experience periodic global resurfacing events, where its entire ice shell fractures and overturns in catastrophic episodes triggered by spin stresses or tidal heating. Another posits that electrostatic forces loft fine ice particles into a temporary atmosphere, allowing winds to redistribute material evenly across the surface, a process observed on Saturn's moon Hyperion, though on a much smaller scale. Then there's the wild-card possibility that Haumea's surface isn't solid ice at all, but a kilometers-thick layer of granular ice particles behaving like a fluidized bed, constantly mixing under the influence of its rapid rotation. The stakes extend beyond Haumea alone. If ice convection operates on this scale, it could redefine our understanding of how mid-sized icy worlds evolve. Europa and Enceladus showcase localized icy geology, but Haumea hints at something far more systemic, a world where the entire surface functions as a single dynamic organ. Yet until we witness this process in action or sample Haumea's ice directly, its unblemished face remains both a triumph of nature and a thorn in the side of planetary physics. The deeper mystery isn't just how Haumea maintains its uniformity, but why it seems to be the only known world doing so with such perfection. Haumea doesn't just stand out for its shape and spin, it's also an orbital rebel, cutting a path through the solar system at a dramatic 28-degree tilt compared to the relatively flat plane where most Kuiper Belt objects reside. This extreme inclination is like watching a lone surfer ride a wave at a near-vertical angle while everyone else glides horizontally. The puzzle isn't just why Haumea orbits this way, but how it managed to maintain such a precarious trajectory for billions of years without being tugged back into alignment by Neptune's gravity or colliding with other objects. The leading explanation points to gravitational scattering, a cosmic billiard scenario where Neptune's migration in the early solar system sent smaller bodies careening into chaotic orbits. As the gas giant drifted outward, its gravity could have acted like a slingshot, flinging Haumea into its steeply inclined path. Computer simulations show this process can produce high-inclination objects, but there's a catch. Most end up with even wilder orbits or get ejected entirely. Haumea's current path is suspiciously stable for something supposedly hurled into chaos. its orbit also crosses the region where Neptune's influence should have either corrected or disrupted it long ago. It's as if Haumea found the one gravitational sweet spot where it could defy the rules indefinitely. Then there's the primordial theory, the idea that Haumea formed this way from the start, emerging from the protoplanetary disk at an angle while the rest of the Kuiper Belt flattened into orderly alignment. This would make it a rare relic of the solar system's birth, preserving the turbulent conditions of that era, but this raises its own questions. If Haumea formed inclined, why don't we see more objects with similar tilts? And how did it retain such a sharp angle while neighboring worlds settled into flatter orbits? Some models suggest Haumea might have been part of a now vanished population of high-inclination objects, most of which were later scattered or destroyed. Complicating matters is Haumea's family of fragments. These smaller objects share its orbital parameters, implying they were once part of the same body. But if a collision broke them apart, why didn't the debris disperse into more typical orbits? The fragments cling to Haumea's unusual inclination like loyal followers, a detail that neither scattering nor primordial theories fully account for. Some researchers speculate that Haumea's unique composition, perhaps an unusually dense core, gave it the gravitational stubbornness to resist orbital damping over eons. Others wonder if an unseen, distant planet in the outer solar system could have anchored Haumea's path, though no such world has been detected. The deeper we dig, the clearer it becomes that Haumea's tilt isn't just a quirk, it's a fingerprint of forces we don't yet understand. Whether through a forgotten gravitational encounter, a primordial fluke, or something even stranger, this dwarf planet's defiant orbit challenges our maps of the solar system's history. Until we uncover more of its secrets, Haumea will keep sailing through the darkness at its own impossible angle, a celestial renegade refusing to follow the crowd. Haumea's dance with Neptune is a gravitational ballet unlike anything else in the Kuiper Belt. While most distant objects drift along without much regard for the giant planets, Haumea moves in lockstep with Neptune through what's called a 7-to-12 mean motion resonance, a precise rhythm where Haumea completes 7 orbits around the Sun for every 12 of Neptune's. This isn't just a cosmic coincidence, it's a delicate balancing act that defies the chaos expected at the solar system's edge. Normally, such complex resonances are unstable, collapsing over time as gravitational tugs disrupt the fragile harmony. Yet Haumea has maintained this syncopated rhythm for billions of years, as if it's found a hidden groove in the fabric of space itself. The rarity of this resonance raises immediate questions. Most resonant Kuiper Belt objects like Pluto follow simpler 2-to-3 or 1-to-2 ratios with Neptune whole number relationships that are easier to maintain. A 7-to-12 ratio is mathematically intricate, requiring near-perfect conditions to persist. Think of it like a metronome set to an irregular beat. Most objects would stumble out of time, but Haumea somehow keeps perfect pace. One theory suggests this stability comes from Haumea's unusually elongated orbit, which may create gravitational sweet spots where Neptune's pulls cancel out over time. Each close encounter could be counterbalanced by subsequent distant ones, like a pendulum swinging back to center, but the real mystery lies in how this resonance formed at all. Current solar system migration models struggle to explain it. When Neptune supposedly drifted outward in the early solar system, it should have shepherded objects into simpler, lower-number resonances. A 7-to-12 ratio implies a series of extraordinarily precise gravitational nudges, like a pinball machine where the ball somehow ricochets into the same impossible slot every time. Some researchers speculate Haumea might have been parked here by an entirely different mechanism, perhaps involving interactions with another now ejected planet or a temporary orbital highway created during the chaos of planetary formation. Others wonder if Haumea's unique shape plays a role, its irregular gravity subtly tweaking its path over eons. The implications ripple far beyond Haumea itself. If complex resonances can persist this long, it challenges our assumptions about how the outer solar system settled into its current arrangement. Migration models may need to account for more nuanced gravitational interplay, or even hidden factors like dark matter's faint gravitational whispers. Haumea's stubborn syncopation is more than a celestial curiosity. It's a metronome ticking to a rhythm we've yet to fully understand. Every orbit it completes is a silent challenge to our theories, a reminder that the outer solar system still holds secrets written in gravity's elusive language. Haumea's density tells a story that doesn't quite line up with its frosty appearance. At 2.6 grams per cubic centimeter, this dwarf planet packs nearly twice the density of pure water ice, an impossible figure for an object that looks like a gleaming cosmic snowball. This discrepancy has scientists scratching their heads because density is supposed to be one of the most straightforward clues about a world's composition. Normally, icy bodies in the Kuiper Belt hover around 1.2 to 1.8 grams per cubic centimeter. Haumea's extra heft suggests there's something far more substantial lurking beneath its shiny exterior. The leading theory points to a hidden rocky core making up as much as 80% of Haumea's mass, a miniature version of Earth's iron-nickel heart buried under kilometers of ice. If true, this would make Haumea's interior structure more akin to Jupiter's moon Ganymede than its Kuiper Belt neighbors, but here's where the math gets tricky. For a core to account for the observed density, it would need to be improbably large and dense, leaving only a thin, icy shell covering the surface. Current models struggle to explain how such a rock-dominated body could form so far out in the solar system, where lighter ices dominate. That's where exotic ices enter the picture. Under extreme pressure, like that found deep inside icy worlds, water molecules can rearrange into strange configurations called high-pressure phases. Ice 6, Ice 7, and even superionic ice have densities approaching or exceeding 2 grams per cubic centimeter. Some researchers speculate that Haumea might contain vast reservoirs of these compacted ices formed during its violent past. A series of ancient impacts could have briefly generated enough heat and pressure to transform ordinary ice into these dense variants, which then persisted as Haumea cooled. The dwarf planet's rapid rotation might help maintain the necessary internal pressures even today. Then there's the dark horse possibility that Haumea isn't as icy as we think. Spectroscopic data clearly shows water ice dominates its surface, but the interior could be a mix of rock and less volatile compounds like iron-rich clays or hydrated minerals. These materials would boost the average density while still allowing for the observed surface chemistry. Imagine a world that's part ice rink, part geological layer cake, with denser strata sandwiched between layers of crystalline frost. The implications reach beyond Haumea itself. If high-pressure ices or unexpected mineral mixes are common in Kuiper Belt objects, it would force us to reconsider how these distant worlds formed and evolved. Current planetary formation models assume a clean separation between icy outer solar system bodies and rocky inner ones. Haumea's stubborn density anomaly suggests the boundary might be far messier than we thought, a reminder that nature rarely follows our neat categorizations. Every new calculation seems to deepen the mystery rather than solve it, proving that even something as basic as density can hide extraordinary secrets when it comes to this cosmic oddball. Haumea's relationship with its outer moon Namaka isn't just a simple gravitational waltz, it's a cosmic mystery wrapped in precise, almost impossible synchronization. Scientists call it spin-orbit coupling, a phenomenon where Haumea's breakneck rotation aligns perfectly with Namaka's erratic orbit in a way that defies the chaos expected from such a lopsided system. Here's the puzzle. Namaka's path around Haumea is wildly elliptical, tilting sharply and shifting unpredictably due to gravitational tugs from both Haumea's irregular shape and the inner moon Hiyaka. Yet somehow, against all odds, Namaka's orbital period locks into a neat 3:1 ratio with Haumea's spin. For every 3 rotations Haumea completes, Namaka makes exactly 1 loop around it. This isn't just an interesting coincidence, it's a configuration so finely tuned. It raises questions about whether we're missing a fundamental piece of this cosmic puzzle. The instability of this arrangement becomes obvious when you break down the forces at play. Haumea's elongated shape creates a gravitational field that's lumpy and uneven, like a mountain range hidden beneath an ocean. Normally, such asymmetry would wreak havoc on a moon's orbit, causing it to wobble, drift, or even collide with its parent body over time. Namaka's path is especially vulnerable because it's so stretched out. At some points, it swings twice as close to Haumea as it does at others. Yet instead of succumbing to this chaos, Namaka's orbit stays eerily synced to Haumea's rotation, as if an invisible hand keeps nudging it back into rhythm. This kind of stability is unheard of in systems with such extreme dynamics. Even Pluto and its moon Charon, which are tidally locked in a much simpler dance, don't exhibit this level of precision under comparable conditions. One theory suggests that Namaka might be trapped in what's called a secular resonance, a delicate balance where subtle, long-term gravitational interactions cancel out the destabilizing effects of Haumea's shape. Think of it like pushing a swing at just the right moment to keep it moving smoothly, even if the pushes aren't perfectly timed. But here's the catch: for this to work, Haumea's interior would need to be unusually rigid, possibly due to a dense rocky core or exotic high-pressure ices, to maintain the consistent gravitational nudges required. Another idea points to Hiyoka's influence. The larger inner moon's gravity might act as a stabilizer, indirectly shepherding Namaka into this unlikely synchronization. Yet simulations struggle to replicate this scenario without the entire system collapsing into disarray within a few million years. The most tantalizing possibility is that we're witnessing a fleeting cosmic moment, a temporary alignment that happens to look stable from our vantage point in time. If true, Haumea and Namaka could be in the slow process of unraveling, their synchronization destined to dissolve over the next 100 million years. But if that's the case, the odds of us catching them in this precise configuration are astronomically low, like stumbling upon a spinning coin balanced perfectly on its edge. Whatever the explanation, Haumea's spin-orbit coupling stands as a testament to the complexity of celestial mechanics. It challenges our assumptions about how small, irregular systems behave and forces us to reconsider the subtle forces that can bring order to chaos. Until we can observe this dance up close, the mystery of Haumea and Namaka's synchronized motions will remain one of the solar system's most elegant enigmas, a reminder that even in the coldest reaches of space, harmony can emerge from the unlikeliest of places. The timeline of Haumea's moons presents a cosmic detective story where the clues refuse to line up. If the leading collision theory is correct that a cataclysmic impact billions of years ago birthed both Haumea's elongated shape and its family of fragments, then its moons Hiyoka and Namaka should be ancient relics weathering the eons alongside their parent body. But their orbits tell a different tale. The dynamics of these moons, particularly Namaka's erratic path and Hiyoka's distant circular orbit, suggest they might be relative newcomers to the Haumean system, possibly forming hundreds of millions or even billions of years after the initial collision. This temporal disconnect forces astronomers to confront an unsettling possibility: that Haumea's history isn't a single violent event frozen in time, but a saga of repeated upheavals stretching across the solar system's lifetime. Hiyoka's orbit alone raises red flags. As the larger outer moon, it circles Haumea in a nearly perfect circle roughly 49,000 kilometers away, a stable configuration that seemingly defies the chaos expected from an ancient impact. Computer simulations show debris from such a violent collision should have either coalesced much closer to Haumea or been flung into wildly eccentric orbits. For Hiyoka to settle into its current path would require either an impossibly precise initial trajectory or some later mechanism to circularize its orbit. One controversial explanation proposes that Haumea might have migrated outward over time, its orbit gradually smoothed by gravitational interactions with Haumea's extended shape or even a now-vanished ring system. But this process would take far longer than the age of the solar system unless aided by forces we haven't yet accounted for. Namaka's behavior deepens the mystery. Unlike its more sedate sibling, this inner moon follows a tilted, egg-shaped path that brings it chaotically close to Haumea before swinging it far out again. Such an orbit is inherently unstable, prone to rapid degradation unless actively maintained. Current models show Namaka's path should have either decayed into a collision with Haumea or been ejected entirely within a few 100 million years, a blink of an eye compared to the solar system's 4.5 billion-year history. The fact that it persists implies either a recent origin or some hidden stabilizing influence. Some researchers speculate that Namaka could be a second-generation moon, a fragment of a larger body that broke apart relatively recently in cosmic terms. Others wonder if Haumea's extreme rotation creates gravitational harmonics that somehow anchor Namaka's precarious dance. The most radical theories challenge the collision narrative entirely. If the moons formed later, perhaps from debris shed by Haumea's rapid spin or a separate, more recent impact, it would mean the original collision family and the moons are unrelated. This would explain the orbital discrepancies but open new questions about why the moons share Haumea's unique ice composition. Alternatively, the entire system might have been reset by a gravitational encounter with another massive Kuiper Belt object, scrambling the moon's orbits while leaving Haumea itself intact. Every possible solution seems to unravel another thread. If the moons are ancient, why do their orbits show such youthful dynamism? If they're young, how did they acquire the same pristine ice signature as Haumea's surface? And what unseen processes could keep such delicate orbital balances in check over vast stretches of time? The contradictions pile up, revealing gaps in our understanding of how small celestial systems evolve. Until a spacecraft visits Haumea to study its moons firsthand, their chronology remains a paradox, a reminder that even the solar system's frozen outskirts are anything but frozen in time. Haumea's thermal emissions read like a fever chart from a celestial hospital, unexpected spikes of infrared radiation that shouldn't exist on a small, frozen world so far from the sun. When astronomers first measured its heat signature across different wavelengths, they stumbled upon a glaring anomaly. Haumea radiates far more warmth at certain infrared frequencies than its icy surface temperature can account for. This infrared excess isn't just a minor discrepancy, it's a full-blown thermal rebellion, suggesting hidden energy sources churning beneath Haumea's glittering exterior. If this dwarf planet were a patient, doctors would be scrambling for explanations because the symptoms defy every standard diagnosis for a body its size and distance. One provocative theory points to radioactive decay deep within Haumea's core. Heavy elements like uranium and thorium, common in rocky planetary interiors, naturally break down over time, releasing heat as they do. On larger worlds like Earth, this process drives plate tectonics and volcanic activity, but Haumea's small size should have allowed most of this heat to escape billions of years ago. Unless, that is, its core is unusually enriched with radioactive isotopes, a possibility that would rewrite what we know about how Kuiper Belt objects formed. Imagine a scenario where Haumea somehow scooped up an extra helping of these elements during the solar system's chaotic infancy, creating a long-lived nuclear furnace beneath the ice. While compelling, this idea struggles to explain why similar excess hasn't been detected around other dwarf planets with comparable compositions. Then there's the tidal heating hypothesis, a cosmic twist where Haumea's own moons might be indirectly cooking it from within. As Haumea and Namaka tug on their misshapen parent, their gravitational pulls could flex Haumea's interior like a stress ball, generating friction heat. This mechanism powers the volcanic fury of Jupiter's moon Io and the subsurface oceans of Europa, but those worlds benefit from Jupiter's immense gravity. Haumea's moons are tiny, and their orbits, while peculiar, don't seem eccentric enough to produce significant tidal forces, unless, of course, we're underestimating their influence. Some calculations suggest that if Haumea's interior contains pockets of slushy or liquid material, even weak tidal strains could amplify heat production through a process called viscoelastic dissipation, where energy builds up like a coiled spring before releasing as warmth. The wild card in this thermal whodunit, crystalline restructuring, Haumea's surface is dominated by highly ordered ice, which requires energy to maintain its neat molecular arrangement against the disordering effects of cosmic radiation. As the ice slowly degrades over time, it might release latent heat, a subtle but persistent energy leak that could account for the infrared excess. Think of it like a freezer working overtime to maintain its temperature. Haumea's ice could be constantly repairing itself at the molecular level, shedding heat in the process. This elegant solution would explain why the excess appears most pronounced at specific wavelengths associated with ice lattice vibrations. Yet laboratory experiments show this effect alone likely couldn't produce the observed temperature spikes. The most tantalizing and controversial idea is that Haumea might harbor residual heat from its formation. Most small bodies cool rapidly after birth, but if Haumea formed through a particularly violent collision, the energy from that impact could have trapped warmth beneath an insulating ice shell. Over billions of years, this heat might be seeping out in sporadic bursts, creating the observed infrared anomalies. It's a stretch, but not impossible after all. We now know even some asteroids show signs of unexpected internal activity long after their formation. Until we can peer beneath Haumea's icy shroud, its thermal excess remains a cryptic signature of forces we can't yet measure. Whether driven by radioactive whispers, gravitational murmurs, or something entirely unforeseen, this tiny world's unexpected warmth is a reminder that even in the solar system's frozen hinterlands, cold is sometimes just a surface illusion. Haumea's spectral lines tell a story that keeps rewriting itself. When astronomers train their telescopes on this distant dwarf planet, they're met with a peculiar phenomenon: water-ice absorption bands that shift strength and shape unpredictably over time. These spectral variations aren't subtle. Some observations show ice signatures twice as strong as others, while certain wavelengths fade entirely for months before reappearing. It's as if Haumea's surface is alive with change, contradicting our expectations for an inert, frozen world in the solar system's deep freeze. But the real puzzle isn't just what's happening, it's why. The first clue lies in the ice itself. Most Kuiper Belt objects display stable water ice features. Their spectra look like frozen snapshots, unchanging over decades. Haumea's fluctuations suggest something dynamic is altering the structure or distribution of its surface ice. One possibility is cryovolcanic activity. If plumes of fresh ice occasionally erupt from beneath the crust, they could temporarily brighten spectral lines before cosmic radiation darkens them again. But this explanation runs into a snag. Haumea lacks the internal heat sources typically required to power such eruptions. Unless its rapid rotation or tidal interactions generate unexpected geothermal energy, cryovolcanism seems implausible. Earth's atmosphere adds another layer of confusion. Water vapor in our own skies can contaminate observations, mimicking or masking ice features on distant bodies. Some researchers argue these variations might be mere observational artifacts, illusory shifts caused by humidity changes at telescope sites rather than actual transformations on Haumea. Yet meticulous studies accounting for atmospheric effects still detect anomalies. When the Gemini Observatory tracked Haumea simultaneously from Hawaii and Chile, eliminating local weather variables, the ice band still wobbled unpredictably. This implies the changes are real, originating from Haumea itself. A more radical idea involves impact gardening. micrometeorites constantly pepper Haumea's surface, churning up fresh ice from below while radiation darkens the exposed layers. Ordinarily, this process would reach equilibrium, creating a steady-state spectrum. But Haumea's extreme spin might amplify the effect. Its rapid rotation could launch ice particles into temporary suspension, creating a flickering veil that alters spectral lines as it settles. Imagine a snow globe shaken by invisible hands, its glittering contents constantly reshaping how light passes through. The wild card, seasonal sublimation. While Haumea's orbit is too distant for significant solar heating, its dramatic axial tilt creates pronounced seasons. Sunlight striking at different angles might trigger localized ice sublimation, exposing darker substrate or fresh ice patches. This would mirror processes seen on Pluto, where nitrogen ice migrates across the surface over decades, except Haumea's water ice requires far more energy to sublimate. Unless unknown compounds lower the ice's volatility, this explanation remains speculative. What makes these spectral variations so maddening is their inconsistency. They don't follow clear cycles or correlate with Haumea's rotation or orbit. Some changes unfold over weeks, others persist for years. It's possible we're witnessing multiple overlapping phenomena, a cocktail of atmospheric interference, surface refreshment, and maybe even internal activity conspiring to keep us guessing. Until a spacecraft can study Haumea up close, its flickering spectral lines will remain one of the solar system's most elusive riddles, a reminder that even the faintest light from the farthest worlds can carry echoes of unseen turmoil. Haumea's surface gleams like freshly fallen snow despite sitting unprotected in the cosmic shooting gallery of the Kuiper Belt for billions of years, a defiance of one of space's most relentless forces, cosmic ray darkening. Every other airless body in the outer solar system, from Pluto to distant Sedna, bears the scars of this slow mutation bombardment, their icy surfaces chemically battered into reddish-brown sludge by endless particle impacts. Yet Haumea stubbornly retains its brilliant white veneer, reflecting sunlight with undiminished intensity as if time itself skipped over this tiny world. The discrepancy is more than puzzling. It's a fundamental challenge to our understanding of how surfaces evolve in deep space. Cosmic rays, high-energy protons and atomic nuclei screaming across the galaxy at nearly light speed act like microscopic sandblasters, breaking apart water ice molecules and reassembling them into complex organic compounds called tholins. These dark, tar-like residues accumulate inexorably, turning once pristine surfaces into dingy carpets over time. Calculations suggest Haumea should have darkened by at least 30% over 4 billion years, yet spectroscopic measurements show less than 5% contamination. This anomaly splits astronomers into two camps, those who believe Haumea's surface is being actively renewed and those chasing far stranger explanations. The renewal theory hinges on cryptic geological activity. If cryovolcanic plumes or ice convection constantly repave Haumea's surface, fresh material could bury radiation-darkened layers before they accumulate. Jupiter's moon, Europa, showcases similar processes where tectonic activity refreshes its icy shell every few million years, but Haumea lacks the tidal heating that powers Europa's geology. Unless its extreme rotation generates unexpected internal friction, a controversial idea, the energy required for large-scale resurfacing remains unaccounted for. Some models propose that Haumea's elongated shape creates stress fractures where subsurface slush oozes upward, like toothpaste squeezed from a tube, but no direct evidence supports this yet. Enter the radical alternatives. One posits that Haumea's crystalline ice structure acts as a self-cleaning shield. Laboratory experiments show that certain ice phases, when bombarded by radiation, can reorganize their molecular lattices and eject impurities, a process akin to sweating out toxins. If Haumea's surface ice exists in an exotic high-pressure state, it might shed dark compounds into space as fine dust, maintaining its reflective purity. Another fringe theory suggests electrostatic forces could be at play. On Saturn's moon Hyperion, charged particles levitate off the surface, creating temporary atmospheres. Haumea's rapid spin might amplify this effect, creating electric fields that eject darkened grains while allowing fresh ice to dominate. The darkest horse explanation. That Haumea's surface is far younger than we assume. If a colossal impact or near-miss encounter stripped away its ancient crust within the last 100 million years, the current surface could be a geological newborn, its radiation clock reset. This would align with the puzzling lack of detectable craters, but contradicts the apparent stability of its spin and orbit. Each hypothesis unravels at the edges, leaving astronomers grappling with a cosmic contradiction. A world that looks eternally new in a universe where everything is supposed to age. Perhaps the most humbling realization is that Haumea's defiance might not stem from a single mechanism, but an improbable confluence of factors: its shape, spin, composition, and history combining to create a perfect anti-aging regimen. Or maybe we're missing something fundamental about how cosmic rays interact with ice at the outer solar system's extreme conditions. Until a probe finally visits this icy enigma, its ageless glow will remain both a beacon and a taunt, a reminder that some of nature's best-kept secrets shine brightest in the darkness. Haumea's moons present astronomers with a cosmic contradiction that threatens to upend our understanding of orbital mechanics. Both Heoka and Namaka follow eccentric, tilted paths that should be stretching and squeezing their interiors through tidal forces, a process that famously keeps Jupiter's moon Io volcanically active and likely maintains subsurface oceans on Europa and Enceladus. Yet when scientists scrutinized these distant satellites for signs of tidal heating, they found nothing. No infrared hotspots, no cryovolcanic plumes, not even the subtle surface fracturing that typically betrays internal flexing. This absence of activity isn't just surprising, it challenges fundamental assumptions about how energy dissipates in icy celestial bodies. The mathematics behind this paradox reveals just how bizarre the situation is. Namaka's orbit brings it nearly twice as close to Haumea at periapsis than at apopsis, creating gravitational differentials that should generate measurable internal friction. Heoka's path, while more circular, still experiences enough variation to theoretically produce tidal warming. Computer models consistently predict at least some heating should occur, estimates ranging from enough to soften subsurface ice to potentially maintaining localized liquid pockets. Yet every observational test comes up empty. It's like watching a car engine rev violently while the temperature gauge stays stubbornly at zero. One possible explanation lies in the moon's composition. Both appear to be porous rubble piles, loose aggregates of ice and rock held together by gravity rather than solid monoliths. This structural difference could radically alter how tidal forces translate into heat. On rigid worlds like Europa, friction builds as solid layers grind against one another, but a rubble pile might absorb this energy through particle shifting, dissipating it as harmless motion rather than concentrated heat. Think of the difference between bending a steel rod, which generates heat at the flex point, versus shaking a bag of marbles where energy disperses through countless collisions. Some laboratory experiments with simulated icy rubble show these materials can indeed dampen tidal effects by an order of magnitude compared to solid ice. Another factor could be Haumea's extreme rotation rate. Most tidally heated moons orbit planets with relatively slow spins, allowing gravitational interactions to build predictably. Haumea's dizzying 3.9-hour rotation creates a rapidly fluctuating gravitational field that might scramble the usual heating patterns. The tidal forces on its moons could be more chaotic bursts than steady rhythms, preventing the sustained energy buildup needed to melt ice. Imagine trying to heat water by alternately cranking a stove burner to maximum, then turning it off. The average temperature might never reach boiling. The wild card in this equation is time. Tidal heating depends not just on current orbits but on their historical evolution. If Haumea and Haumea only recently settled into their present configurations, perhaps after gravitational interactions pushed them outward from closer orbits, they may simply not have had enough time to accumulate detectable heat. Some simulations suggest the moons could have spent most of their existence in more circular paths, only developing eccentricity within the last few 100 million years. This young heating scenario would make the lack of observable effects less puzzling, though it raises new questions about what triggered such recent orbital changes. The implications extend far beyond this oddball system. If standard tidal models fail to explain Haumea's moons, we may need to reconsider predictions about icy worlds throughout the solar system and beyond. Exoplanet scientists often use tidal heating estimates to assess potential habitability of distant moons. Could we be overestimating their warmth based on flawed assumptions? Haumea's silent satellites serve as a sobering reminder that the universe always has new lessons to teach, even about processes we thought we understood. Their cold stillness speaks volumes about how much we still have to learn. Haumea stands alone in the cosmic dark, a glaring exception to one of the Kuiper Belt's most curious trends. Nearly every other large object in this frigid realm, from Pluto to Makemake, dances in gravitational partnership with a binary companion. These pairings range from near equals like Pluto and Charon to more lopsided arrangements where a tiny moon orbits a dominant primary. Yet Haumea, despite its size and prominence, has no such partner. Its two known moons, Haumea and Haumea, are clearly underlings, tiny attendants rather than co-dominant companions. This absence isn't just a trivial detail. It's a gaping hole in our understanding of how Kuiper Belt objects form and evolve, forcing us to question whether Haumea's solitude is an accident of history or a clue to something far stranger. The binary paradox cuts to the heart of planetary formation theories. Current models suggest that most large Kuiper Belt objects should have formed or acquired companions through one of two pathways. The first involves gentle gravitational capture during the solar system's chaotic youth, where two drifting bodies subtly slow each other's motion until they become gravitationally bound. The second points to violent impacts like the one thought to have birthed Earth's moon, where collision debris coalesces into a substantial partner. Both processes should have left Haumea with a binary twin, yet neither seems to have played out. Statistically, the odds of a large Kuiper Belt object lacking a significant companion are staggeringly low, less than 5% based on current surveys. So why is Haumea the exception? One possibility is that Haumea did once have a proper binary partner, but lost it in the aftermath of the cataclysmic collision that shaped its present form. Simulations show that high-energy impacts can sometimes destabilize existing moon systems, either by altering the parent body's rotation or by providing enough kinetic energy to fling companions into space. If Haumea's ancient collision was particularly violent or asymmetrical, it might have ejected a former co-orbital partner entirely, leaving behind only the smaller debris we now see as its moons and family members. Supporting this idea is the curious case of 2002 UX25, another Kuiper Belt object that appears to have divorced its binary companion after a disruptive event. Could Haumea represent a more extreme version of this same process? Not everyone agrees with the lost companion narrative. Some dynamicists argue Haumea might never have had a binary partner to begin with, its formation pathway differing fundamentally from its neighbors. One radical hypothesis suggests it could be a transplanted interloper, a former satellite of Neptune or Uranus that was ejected outward during the gas giant's orbital migrations. Such objects might lack binaries due to their chaotic histories, having been stripped of companions by close encounters with their massive former hosts. Yet this theory struggles to explain Haumea's compositional match with its collisional family. If it originated near the ice giants, why does its ice signature so closely match other Kuiper Belt natives? The implications ripple through multiple disciplines. From an observational standpoint, Haumea's loneliness forces us to reconsider how we define binary systems, and whether our current detection methods might be missing faint or distant companions around other objects. Dynamically, it challenges assumptions about angular momentum distribution in the early solar system. Without a binary partner to share rotational energy, Haumea's extreme spin becomes even harder to explain. Most intriguingly, its solitary state might hint at unseen processes that can dismantle binary systems over time, whether through collisions, gravitational scattering, or something more exotic. As telescopes grow more powerful, astronomers continue searching for any trace of a lost companion, perhaps a distant, lazily orbiting body not yet detected, or spectral evidence of a now-vanished partner in Haumea's family fragments. Until then, this dwarf planet's isolation remains one of the Kuiper Belt's quietest yet most profound mysteries, a silent testament to the dynamic and sometimes destructive forces that shaped our solar system's frozen fringe. Haumea's refusal to follow seasonal conventions is as baffling as its other quirks. With an axial tilt of 28 degrees nearly identical to Earth's, you'd expect this dwarf planet to experience pronounced seasonal cycles as different hemispheres tilt toward the distant sun. Yet observations reveal no detectable changes in brightness, temperature, or surface composition over time. This absence of seasons stands in stark contrast to Pluto, where nitrogen snows blanket entire hemispheres as sunlight shifts, and methane frosts sublimate into temporary atmospheres. The question isn't just why Haumea lacks seasons, but how it suppresses what should be an inevitable cosmic rhythm. Pluto's dramatic transformations offer a revealing counterpoint. As it swings along its elliptical orbit, sunlight intensity varies by 30%, driving nitrogen and methane ices to migrate across its surface in planet-scale climate cycles. These volatile compounds sublimate readily even at Pluto's frigid temperatures, creating observable shifts in albedo and atmospheric pressure. Haumea, however, seems locked in perpetual stasis. Its orbit is more circular than Pluto's, minimizing solar exposure variations, but that alone can't explain the complete lack of response. The real culprit may lie in the chemistry of its surface. While Pluto's volatile ices behave like weather-sensitive powders, Haumea's dominant water ice is far more stubborn. It requires temperatures Haumea never reaches to sublimate significantly. Without this phase-changing engine to drive seasonal processes, Haumea's climate becomes a flat line, but the plot thickens when we consider internal heat. Seasonal effects can be amplified or suppressed by geothermal energy. Think of how Earth's ocean's moderate temperature swings. If Haumea harbors subsurface warmth, as some thermal anomalies suggest, this heat could theoretically smooth out any faint seasonal variations before they become observable. Yet this creates a paradox. Internal heat would also be expected to drive other dynamic processes, like cryovolcanism or surface renewal, which we don't conclusively see. Alternatively, Haumea's bizarre shape might play a role. Its elongated form creates uneven thermal inertia. The equatorial bulge, spinning rapidly under constant sunlight, could act as a thermal buffer, absorbing and redistributing energy in ways that mute seasonal contrast. The implications reach beyond academia. If Haumea truly lacks seasons despite conditions that should produce them, it challenges our definitions of planetary climates. We're forced to confront the possibility that some worlds exist in a perpetual state of equilibrium, their surfaces deaf to the rhythms that govern most celestial bodies. This isn't just a missing weather pattern, it's a fundamental gap in our understanding of how energy flows across icy worlds. Until we witness Haumea's slow dance around the sun up close, its seasonless existence will remain a quiet rebellion against our expectations. Haumea's surroundings are suspiciously clean, a cosmic bedroom that somehow never collects dust no matter how much time passes. In the bustling construction zone of the Kuiper Belt, where micrometeorites rain down constantly, every object should be surrounded by a faint halo of debris. Yet when astronomers search for dust around Haumea, they come up nearly empty-handed. This absence isn't just odd, it's a direct violation of expectations. After 4 billion years of collisions, Haumea's neighborhood should resemble a poorly vacuumed living room, not a sterilized laboratory. The clean zone extends far beyond what its gravity could explain, hinting at some unseen force actively scrubbing the environment. The most straightforward explanation that Haumea simply isn't being hit falls apart under scrutiny. The Kuiper Belt teems with debris, and at Haumea's size, it should endure thousands of detectable impacts every year. Each strike, no matter how small, should blast surface material into orbit, creating a steady supply of dust. Yet observations from infrared telescopes to stellar occultations reveal no detectable ring or cloud of particles. Even accounting for Haumea's rapid rotation, which might fling some ejector into interstellar space, the deficit remains staggering. This forces scientists to consider far more exotic possibilities. One compelling theory points to electrostatic forces. On airless worlds like Earth's moon, sunlight charges surface dust grains through the photoelectric effect, causing them to levitate and drift. Haumea's crystalline ice, combined with its extreme spin, might amplify this process into a full-blown cleaning mechanism. Imagine each micrometeorite impact kicking up a spray of ice particles, only for them to become electrically charged and get catapulted away by the dwarf planet's rotating magnetic field, assuming Haumea has one. Laboratory experiments with icy analogs show certain crystal structures can generate surprisingly strong electrostatic fields when fractured, especially under ultraviolet light. If this effect operates at planetary scales, Haumea could essentially be repelling its own dust like a cosmic-scale air purifier. An alternative idea suggests Haumea's surface might simply produce less dust than expected when hit. Most impacts on icy bodies create fine debris through a combination of shattering and vaporization. But if Haumea's subsurface contains unusual materials, perhaps layers of unusually tough, ductile ice or even unexpected voids, impacts might behave differently. Instead of generating clouds of fine particles, collisions could produce larger chunks that quickly fall back to the surface or cohesive clumps resistant to pulverization. Some researchers speculate that Haumea's high-pressure ice phases might even self-heal after impacts, minimizing debris production through plastic deformation rather than brittle fracture. The wild card in this enigma, Haumea's ring, while counterintuitive, the presence of a narrow, dense ring might actually help explain the broader dust deficit. Ring particles could act as gravitational shepherds, sweeping up or ejecting stray dust grains before they can disperse. Alternatively, the ring itself might be the key to the cleaning mechanism. If its particles are electrically charged, their collective field could create an invisible barrier that deflects incoming dust or accelerates its ejection. This would make Haumea's system a delicate balance between creation and destruction, where impacts feed the ring while the ring prevents debris from spreading. The implications stretch beyond Haumea alone. If electrostatic clearing or impact-resistant surfaces are real phenomena, they could explain similar dust deficits around other icy bodies. Europa and Enceladus, despite their geological activity, also show puzzlingly clean orbits. Even Earth's moon has subtle electrostatic dust fountains that might hint at a scaled-down version of Haumea's process. Until we can study this distant world up close, its immaculate surroundings will remain both a lesson in orbital housekeeping and a reminder that nature always finds unexpected ways to defy our assumptions. Haumea's microwave emissions reveal a secret language written in radiation, one that tells a story our telescopes can barely decipher. When astronomers first studied this distant world using radio telescopes, they expected smooth, symmetrical thermal radiation, the kind emitted by most icy bodies as their interiors gradually cool. Instead, they found bizarre hotspots and cold zones flickering across Haumea's surface, creating a lopsided thermal fingerprint that changes unpredictably over time. These aren't minor fluctuations. Some regions emit up to 20% more microwave energy than others, a disparity that defies straightforward explanation. It's as if someone installed hidden heaters beneath certain patches of Haumea's icy crust while leaving neighboring areas in deep freeze, a cosmic-scale thermostat gone haywire. The first clue to this mystery lies in how microwave radiation behaves. Unlike visible light that bounces off surfaces, microwaves penetrate deeper, carrying information about subsurface layers typically tens to hundreds of meters below the crust. The uneven emissions suggest Haumea's interior isn't uniformly structured like a simple ice ball, but rather a patchwork of different materials and densities. One leading theory proposes large-scale chemical differentiation, an underground landscape where vast regions of pure water ice border slushy mixtures of ammonia hydrates or salts. These compounds would conduct and retain heat differently, creating the observed thermal mosaics. Imagine an iceberg where one side is solid while the other contains pockets of briny water, except on Haumea, these variations might span entire continents. Even more intriguing is the possible role of Haumea's extreme shape. Most planetary bodies radiate heat symmetrically because their spherical forms distribute internal stresses evenly. But Haumea's stretched ellipsoid shape creates unbalanced gravitational pressures, immense compression at the poles versus tension along the equator. This could drive irregular heat flow, channeling geothermal energy towards certain regions while starving others. Some models suggest these forces might even fracture the icy shell into tectonic plates of varying thickness, with thin areas bleeding heat faster than thick insulating zones. Picture a cracked eggshell where the yolk's warmth escapes unevenly, except here, the yolk might be a still warm rocky core leftover from Haumea's violent formation. The wild card in this thermal puzzle, crystalline alignment. Haumea's surface ice isn't randomly oriented. Its molecules align in consistent lattices due to the dwarf planet's rapid spin. This ordered structure could act like fiber optic cables for heat transfer, directing thermal energy along specific axes rather than radiating it uniformly. Certain microwave hotspots might mark where these thermal highways breach the surface, while cold spots could indicate areas shielded by crosswise crystal layers. Laboratory experiments with oriented ice crystals show they can exhibit wildly different thermal conductivities depending on measurement direction, a property that, at planetary scales, might explain Haumea's radiation quirks. These anomalies aren't just academic curiosities, they're potential game changers for how we understand icy worlds. If Haumea's interior is indeed this heterogeneous, it challenges the standard model of Kuiper Belt objects as chemically uniform leftovers from the solar system's birth. Instead, we might be looking at a world that underwent complex geological evolution, with internal melting and differentiation processes we thought impossible for such small bodies. The uneven microwave whispers from Haumea's depths could be the first hints of a dynamic underworld hiding beneath its icy mask, one that refuses to conform to our expectations of what a dwarf planet should be. Haumea's past might be written in celestial hieroglyphs, clues hidden in its orbit and chemistry that point to an origin far from its current frozen outpost. The evidence is mounting that this oddball dwarf planet didn't form in the Kuiper Belt at all, but much closer to the Sun before being violently ejected to the solar system's fringes. Like a cosmic archaeological dig, scientists piece together this migration tale through subtle inconsistencies, compositional fingerprints that don't match its neighbors, orbital dynamics that defy local patterns, and a family of fragments that seem too pristine for the Kuiper Belt's rough and tumble environment. Start with the chemistry. Haumea and its kin shine brighter than any other known Kuiper Belt objects. their surfaces dominated by remarkably pure water ice with spectral signatures identical to ice found on Jupiter's moons Ganymede and Callisto. This is wildly out of place. Most Kuiper Belt objects show darker, chemically processed surfaces, their ices dulled by billions of years of cosmic radiation and laced with organic compounds. Haumea's ice looks freshly poured, as if it solidified under very different conditions than its current surroundings. Even more telling is the presence of crystalline ice, which typically requires temperatures above -150 degrees Celsius to form, far warmer than the Kuiper Belt's perpetual deep freeze. This suggests Haumea's surface ice originally crystallized much closer to the Sun, where solar heating could maintain those conditions before being abruptly transported outward. The orbital forensics are equally compelling. Haumea's present path carries it from 35 to 51 astronomical units from the Sun, but its gravitational resonances with Neptune hint at a more chaotic past. Dynamicists have long known that Neptune's outward migration in the early solar system scattered smaller bodies like cosmic billiard balls. What's surprising is how precisely Haumea's current orbit aligns with simulations of objects ejected from the region between Uranus and Neptune. Its 7-to-12 resonance with Neptune, an intricate gravitational lockstep, is far easier to explain if Haumea originated in the giant planet zone, where complex orbital interactions were commonplace. Yet the migration theory isn't without holes. If Haumea formed nearer to the Sun, why doesn't it show signs of ammonia or methane ices common in that region? These volatile compounds should have been abundant in its birthplace, yet they're conspicuously absent. One provocative solution proposes that Haumea's parent body was already chemically distinctive, a rare, volatile poor planetesimal that avoided contamination during its journey. Another puzzle is timing. For Haumea to reach its current orbit, the ejection must have occurred during Neptune's planetary migration phase, roughly 4 billion years ago. But Haumea's surface appears geologically young, with few craters and active resurfacing processes that suggest recent turmoil. Did something reheat or refresh Haumea long after its arrival in the Kuiper Belt? The most radical ideas challenge conventional solar system history altogether. Some researchers speculate Haumea might be a captured rogue object, a wanderer from another star system, though its spectral match with local ice makes this unlikely. Others suggest it could be a remnant of a shattered ice giant moon, blasted apart during the solar system's violent youth. The wildest theories even invoke gravitational perturbations from a hypothetical planet 9 to explain Haumea's peculiar orbit. What's clear is that Haumea refuses to fit neatly into any origin story. Each clue points to a dramatic journey, a celestial odyssey from warmer climes to the frozen dark, but the exact route remains shrouded in mystery. Until we can sample its ice or trace isotopic signatures back to a birthplace, Haumea's past will continue to taunt us with half-told tales of upheaval and exile. Haumea's future plays out like a high-stakes cosmic balancing act, one where the slightest misstep could trigger a chain reaction of celestial chaos. Given its extreme rotation, peculiar moons, and gravitational quirks, this dwarf planet exists in a state of precarious equilibrium, making predictions about its ultimate fate as uncertain as they are dramatic. The most immediate threat comes from its relentless spin. Clocking in at just under 4 hours per rotation, Haumea teeters on the knife's edge of stability. Calculations suggest that if its speed increases by even 10%, centrifugal forces could overpower gravity, sending its surface ice and potentially its entire structure spiraling into space. This isn't just theoretical. We've watched smaller asteroids like P/2013 R3 disintegrate under similar rotational stress. The difference: Haumea's immense size means its breakup wouldn't be a quiet fade-out but a spectacular, slow-motion explosion of ice and rock. Then there's the question of its moons. Hiyoka and Namaka orbit in a delicate gravitational dance that could easily be thrown off kilter. Namaka's erratic path, in particular, sits on the brink of instability. Some simulations show it drifting too close within the next 100 million years, triggering one of two catastrophes, either a collision that would shatter both moon and dwarf planet, or a gravitational slingshot that ejects Namaka into the void. The latter scenario could leave Haumea spinning even faster, like a figure skater pulling in their arms, potentially hastening its own demise. Alternatively, the moons might gradually spiral outward, leaving Haumea alone and unchallenged. But given its history of chaos, a quiet retirement seems unlikely. The wild card in this cosmic forecast is Haumea's strange internal structure. If it harbors dense layers of exotic high-pressure ice or a partially molten core, these could act as shock absorbers, prolonging its lifespan against rotational stresses. Conversely, if its interior is more fractured or porous than we suspect, a single large impact might cause it to unravel like a poorly stitched snowball. There's also the lingering mystery of its spectral variations. If they truly indicate ongoing geological activity, Haumea could be actively regenerating itself against these destructive forces. But perhaps the most intriguing possibility is that Haumea's fate is already sealed by forces we can't yet measure. The faint gravitational whispers of undiscovered Kuiper Belt objects or even the hypothetical Planet 9 could be subtly reshaping its orbit, guiding it toward an unknown destiny. Or maybe, against all odds, it will continue its defiant spin for billions more years, a cosmic outlier refusing to play by the rules until the sun's final expansion consumes it. The only certainty, however Haumea meets its end, it won't be quietly. This dwarf planet has spent its existence breaking molds. Its finale will likely shatter them entirely. Haumea's bizarre collection of anomalies isn't just a cosmic curiosity, it's a wrecking ball swinging at the foundations of planetary science. Every textbook chapter on dwarf planet formation assumes these distant worlds should be frozen time capsules, simple and predictable. But Haumea shreds those assumptions with its impossible spin, its warped shape, and its enigmatic family of fragments. Take the standard model of collisional evolution, the idea that impacts in the Kuiper Belt create predictable debris patterns. Haumea's shattered family defies every simulation, spreading fragments across orbits that shouldn't be stable while leaving gaping voids where debris should be. This isn't just a case of missing puzzle pieces, it's evidence the entire puzzle might be assembled wrong. The implications ripple through our understanding of icy body physics. Conventional models assume objects Haumea's size should behave like rigid spheres, their shapes governed by gravity's smoothing influence. Yet Haumea's extreme elongation proves mid-sized worlds can maintain irregular forms indefinitely, forcing physicists to reconsider how internal strength and rotational forces compete at planetary scales. Its existence suggests a hidden population of cosmic potatoes might lurk undetected, overlooked because our telescopes have been programmed to search for near-perfect spheres. Even more radical is the possibility that Haumea's structure relies on exotic ices with bizarre material properties, substances that could rewrite our playbook for everything from moon formation to exoplanet interiors. Then there's the revolution brewing in orbital dynamics. Haumea's delicate 7 to 12 resonance with Neptune shouldn't persist in such a chaotic environment. Standard migration models struggle to explain how such a complex gravitational ballet survives billions of years without collapsing. This isn't just about one odd dwarf planet. It hints that our entire framework for how small bodies interact with giants like Neptune might be oversimplified. Perhaps resonances are far more resilient than we thought, or maybe unseen forces like dark matter's subtle tug or the gravitational whispers of undiscovered planets are quietly orchestrating these orbits. Most startling of all is how Haumea challenges the very definition of geological activity. Frozen worlds this small and distant were supposed to be geologically dead, their internal heat long since dissipated into space. Yet Haumea's infrared excesses, its pristine surface, and its possible cryovolcanic hints suggest that energy can be stored, focused, and released in ways we never imagined for icy bodies. This forces a paradigm shift. Instead of viewing dwarf planets as inert fossils, we might need to consider them as dynamic worlds with hidden energy budgets, places where tidal forces, radioactive decay, and even crystalline restructuring could power unexpected upheavals. The deepest lesson Haumea teaches is humility. For centuries, we've assumed the outer solar system to be a calm, orderly place where physics behaves predictably. But this spinning, stretched, hyperactive dwarf planet screams otherwise. It stands as proof that even in the darkest, coldest reaches of our cosmic backyard, nature still has tricks we haven't dreamed of, and that every time we think we've got the universe figured out, something like Haumea comes along to remind us how much we've yet to learn. Unlocking Haumea's secrets will require humanity to pull off one of the most audacious deep space missions ever attempted. Unlike Pluto, which New Horizons flew past in a matter of hours, Haumea's breakneck rotation and extreme shape demand an entirely new approach to exploration. Imagine trying to photograph a spinning top while riding a roller coaster. That's the challenge spacecraft designers face. Current mission concepts revolve around two key strategies: a high-speed fly, optimized for snapshots of this tumbling world, or an orbital ballet so precise it could synchronize with Haumea's chaotic rotation. The European Space Agency's Castalia proposal, though shelved, laid crucial groundwork. A spacecraft equipped with thermal mappers to probe subsurface heat and spectrometers capable of detecting organic molecules hidden in that gleaming ice. The technical hurdles are staggering. Haumea's 4-hour rotation means any orbiting probe would need to adjust its trajectory constantly, burning through fuel at unsustainable rates. Engineers speculate a hybrid approach might work using solar electric propulsion for gradual course corrections combined with gravity assists from Haumea's moons to stabilize the orbit. Another radical idea involves deploying surface penetrators timed to strike during the dwarf planet's brief, flat presentation, when its elongated shape offers a more stable impact zone. These dart-like probes could seismically scan the interior while surviving just long enough to radio back data before centrifugal forces tear them apart. Instrumentation choices reveal how much we still don't understand. A millimeter-wave radar could settle the debate over Haumea's internal structure by differentiating between solid rock, slushy ice, and possible liquid pockets. Laser altimeters would map surface topography down to centimeter resolution, revealing whether that uncanny smoothness hides fractures or cryovolcanic flows. But the crown jewel might be a neutron spectrometer, a device that could detect hydrogen signatures from possible subsurface oceans, solving the mystery of those infrared hotspots once and for all. Timelines stretch far into the future. Even with an ideal launch window, a Haumea mission would take 12 to 15 years using conventional propulsion, longer than the entire Cassini mission at Saturn. NASA's upcoming interstellar probe concept targeting the 2030s might include Haumea as a secondary objective if trajectory adjustments prove feasible. Private initiatives like Breakthrough Starshot's nanocraft could theoretically reach Haumea within decades using laser sails, though their tiny payloads would limit scientific returns. What makes these challenges worthwhile are the potential revelations. Confirming the existence of high-pressure ices could rewrite textbooks on planetary formation. Discovering tidal heating in Haumea's moons might redefine the habitable zone's outer limits. And if by some cosmic fluke that crystalline surface hides probiotic chemistry, we'd have to reconsider where life might emerge in solar systems. Every unanswered question about this spinning enigma isn't just a gap in our knowledge, it's a beacon calling us to push the boundaries of exploration further than ever before. The day we finally see Haumea up close won't just solve mysteries. It will reveal how much we've underestimated the dynamism of the solar system's frozen frontier. Haumea stands as one of the solar system's greatest enigmas, a cosmic rebel that refuses to play by the rules. From its dizzying 4-hour spin that should tear it apart to its ghostly ring that defies orbital mechanics, every layer of this dwarf planet challenges our understanding of how celestial bodies behave. Its gleaming, craterless surface looks brand new against the battered backdrop of the Kuiper Belt, while its mismatched moons orbit in impossible synchrony. Even its origin story is a mess of contradictions, a collisional family that shouldn't exist, a density that hints at secrets buried deep beneath the ice, and an infrared glow that suggests hidden warmth in the coldest reaches of space. What makes Haumea so compelling isn't just the individual mysteries, it's how they intertwine, each anomaly deepening the others. The same cataclysmic impact that may have stretched it into a football shape could explain its moons, yet their orbits don't match the simulations. Its crystalline ice surface should have darkened billions of years ago, yet it shines like a cosmic mirror untouched by time, and that faint, narrow ring. It's not just an oddity, it's a violation of physics surviving against all odds in the chaos of Haumea's gravity. Every answer we think we have only leads to deeper questions, leaving scientists to wonder if we're missing an entire chapter in the book of planetary formation. So what's really going on out there in the dark? Could Haumea's interior harbor exotic materials we've never encountered? Might its spin be powered by forces we don't yet understand? Or is it possible this isn't even a native of the Kuiper Belt at all, but a refugee from some long-forgotten collision in the inner solar system? The more we study this tiny world, the clearer it becomes Haumea isn't just an outlier. It's a cosmic puzzle box, and every layer we peel back reveals another twist in the story. Now it's your turn. What do you think lies beneath Haumea's icy shell? A hidden ocean, a shattered core, or something even stranger? Drop your wildest theories in the comments, because in a universe full of mysteries, Haumea might just be the one that rewrites the rules. And if you love diving into the unknown with us, don't forget to subscribe. Who knows what other cosmic oddities are waiting to be uncovered?